First of all, I'm very glad to be here to share my research and my research interest with you today. And thank you for coming. I will start with the motivation of my research, explain why low power consumption is important in frequency synthesis. And then we will proceed with two design, can you hear? Two design examples. One is analog FBAR PL, the other is analog digital FBAR PL. And I will explain what FBAR is later. Before I do the conclusion, I will briefly talk about my future research direction. We've seen many applications or many potential applications of wireless sensing. Here are a few of them. The first one shows a cochlear device that can be implanted into a deaf person's ear. And we use this device to help a deaf person to gain hearing. The second example shows a bird carrying a tiny wireless device, recorder, and that can help a scientist to study the behavior of wild birds. The third one shows an application in agriculture. For example, we can use a moisture sensor to sense the moisture so that we can direct the irrigation system. The last one shows a tire pressure sensor that is installed on a vehicle tire. So basically, all these sensors share the same trait. They collect data, sense the data from its environment, and then do some digital or analog signal processing, and then transmit wirelessly to a network. A wireless sensor network, wireless sensor basically consists of the following building blocks. The first one is an energy source. It can be a battery, can be energy harvester, or can be other means of energy source. The second one is transducers or sensors. And this can be made in semiconductor process, MEMS process, some other processes. And it can be biosensor, can be chemical sensor, can be any physical sensors. And the rest of the blocks are circuits. We have power management in there, mixed signal interface to those sensors, and data processing. And the rest of the blocks are for transmissions. And it has baseband and then RF front end. All these blocks, the circuit blocks, can be integrated in one single IC chip. And the sensors usually requires you have a very small form factor. In many applications, it's very desirable to have the form factor to be around in the order of 1 centimeters cube. And we need to power this thing in very low power, extreme low power. And obviously, we have to integrate these things across different processes. So let's first examine how much power that is available in this tiny volume that we wish to accomplish. If we use a battery to power the system, if we assume the power consumption in the electric circuits is 100 microwatt, the battery can last only about a year. And that's not acceptable in many applications. And we have options for energy scavenger. And with thermal gradients, the maximum power probably is available at around 150 microwatt. And with vibration, 3 milliwatts, solar, 15 milliwatts, wind, 2 milliwatts. Keep in mind, these numbers are all quoted at the most favorable conditions. For instance, solar energy, we have to put the device into a full sun to be able to get the full maximum power. So when we are talking about a device size so small, basically we are talking about the available power from harvesting is about at the order of 1 milliwatts or 2 in that kind of order. So let's see how much power actually is needed for wireless sensors. So we examine one example, industry example, which is available in market from TI. It's a low power transceiver. And in both transmit and receive modes, we need 30 milliwatts to operate. So that gave you a little bit of flavor about how much power that is needed in transmission and receiving. And we see the big discrepancy in here, power consumption and how much power we actually needed. So I'm circuit designer, so I'm interested in bringing down this power so that we can realize these wireless sensors. So to start with my project, first thing I needed to see what exactly going on and where the power goes. So we examined one Zigbee device, and that device has a digital portion and RF front end. And the digital portion consumes 1/3 approximately of the power, and the rest consumed most of the power. And within the rest of this RF front end, phase-lock loops consumes half of the power. So that's what I do. Try to reduce the power in phase-lock loops so that we can bring down the total power. And additionally, we don't care about digital power in here because I was assumed that as process scales, digital power will be becoming less and less because digital circuit is made more and more efficient as we move down to a newer process. So to understand why PLL consumes so much power, let me explain what it does in the transceiver for PLL. So this shows a very fundamental kind of basic structure for the transceivers. We have two paths. One is a receive path, another is transmit path. A sinusoidal signal that is very much needed in this kind of operations, down conversion, up conversion. And that sinusoidal signal is this local oscillator signal, LO signal. And that signal is used to down convert your received signal from antenna RF signal, that's a high frequency signal, and convert into intermediate frequency so that the baseband can do the processing. And that's IF signal is the signal that we want eventually received. And in the transmit side, we do the similar thing, but we modulate up the intermediate frequency to a RF frequency. So this PLL, what PLL does here is it produce this local oscillator signal. So let's see, in this PLL, we usually have an oscillator in there to generate that sinusoidal signal. In this oscillator, we have usually use a resonator to generate the oscillator signal. And commonly, we use L and C tank to generate that oscillator signal. Ideally, this LC will generate very defined tune in here, indicated by FC. That is a resonant frequency. It has a zero bandwidth, and it has an infinite impedance. But when we have loss, which is, for example, you have resistance in there when you build the coil, then that is a model to use this. And then you will see in the impedance curve, the bandwidth will be wider. Usually we define the quality factor of the tank using Q here. It's defined by the resonant frequency divided by the bandwidth. So we see that when we have a more resistive inductor here, then we will have higher, lower quality factor. A sinusoidal signal, when we see in the spectrum domain, it is a pure tone, one line in here. If we see, if we have noise in that sinusoidal signal, then we see the noise skirt in here. And we use phase noise to express how clean this local oscillator signal is. So X direction shows frequency offset, Y direction shows the power relative to the carrier. So phase noise actually exists in all real oscillators. So oscillator always has loss. And if we want to achieve lower phase noise, we can do two things. One thing is to use a higher quality resonator. The other is to use to make the oscillator run more power. And that more power hopefully bring up a stronger carrier so that we can have a better phase noise. So in cases that we have small quality factor available, then we're stuck and we still need a low phase noise. Then in that case, we have to consume more power and in order to get that phase noise. Previously, we saw the local oscillator signal mixed up with RF signal in the receiver. It will generate an intermediate frequency in here. That's a mixer and filter. If we have noise in this local oscillator, then during this mixing, the LO noise will be mixed down into this desired frequency band. That's what we are going to receive. And that degrades the signal to noise ratio. Furthermore, if we have interferers sitting in the next channels, then that interferer will bring up more noise from the local oscillator and adding on top of that already existing noise, further degrading the signal to noise ratio. So that means if we, in transceivers, phase noise from LO matters so much your performance. So if you want to have no very good transceiver sensitivity, if you want to have a good throughput, you have to have very clean local oscillator signal. So how do we actually, most people generate the local oscillator signal today? Here I show a picture that's from last year's conference. We usually use the on-chip inductor and on-chip capacitor to generate the local oscillator signal. So on-chip inductor, here we can see it's made on top of the metal stack in the CMOS process. It's made in a planar process. So it is a two-dimensional structure. It uses a thin layer of metal to do this wiring. So we can see it is very resistive. And in other words, the quality factor of this inductor is very low. When we do process scaling, we focus our energy in trying to bring down the power from digital circuitry and make the transistor smaller and smaller and more efficient. But we rarely do anything in the process side to increase the quality factor of the inductor. So that's the big reason we see a big trade-off between power and phase noise. In order to get low phase noise, we have to consume so much power. That's why we see so much power that is in the phase lock loop design. And this power will not go away if we don't do anything, and it will still keep going on. So how do we break up this power and phase noise kind of the game? Okay. So here I think it's time for me to explain what FBAR is and why I think there's an opportunity here. The FBAR is a bulk acoustic wave resonator. It is made on the silicon wafer using planar process. And it has, the basic structure has 3 layers, 2 layers of electrodes and another layer piezoelectric material. The size in the lateral direction, in the lateral plane, it is 100 by 100, around 100 by 100 micron square. The resonant frequency is determined by the vertical size. In this case, is the thickness of the piezoelectric material. Usually, the frequency is around several hundred megahertz to several gigahertz. In comparison to an on-chip LC, the size of on-chip inductor is bigger than the size of the resonator. The quality factor for on-chip is less than 20, and for this FBAR is more than 1,000. And this big difference can also be intuitively seen in this plot, which is an impedance plot we've seen earlier. X-axis is the frequency, and y-axis is the impedance amplitude. This resonator, the difference from this LC is it has 2 resonances. One is a series resonance that's sitting down here, and frequency is a bit lower. And another is parallel resonance. And this structure looks like a capacitor if we remove this portion of the circuitry, the frequency. So basically, if you operate the structure in lower frequency or higher frequency, it is a capacitor. But if you operate in between the two resonant frequencies, it is a big high quality factor inductor. So we see from here visually that the bandwidth of these two resonance red curve is wider than the blue curve. So that means the quality factor of on-chip inductor is much smaller. At the moment in the integration with CMOS, we need a special process to do the integration if we want to use this FBAR with CMOS. So my approach is use FBAR to replace on-chip inductor. We hope to, we basically go after the high quality factor. Let me first introduce a little bit phase log loops before I start my real work. A phase log loop is commonly used in electronic design. So every electronic is probably your computer, your cell phones. For example, cell phones probably have 10 of them in there. So it's kind of golden standard. Everybody is doing that. The reason for doing that is the oscillator in the phase log loop is not stable. And if you let it free run, and the output frequency will be drifting around over time. And that frequency is useless in the system. So crystal, in contrary, it's stable. You know, when your environment changes, the frequency rarely changes. So that's the characteristic that we use. And we use phase log loop to lock this unstable frequency to this stable frequency. So the way we do it is to use a feedback loop. It's a negative feedback loop. At the output, that's the frequency that we want. That's a carrier frequency, whatever frequency that you use in your system. And then this frequency, of course, is a crystal oscillator frequency. In the feedback, we have frequency. The VCO is a voltage-controlled oscillator because we want this VCO to be able to lock to the crystal oscillator. So we design the oscillator so that it can be controlled using a voltage, so that we can do the feedback. The feedback has a divider which divides down a higher frequency to a lower frequency, which is at a proximity of FREF. And the PFD here is trying to detect phase difference and then output a signal to direct the charge pump and the loop filter to charge up or down the control voltage. And then that control voltage directs this VCO to move faster or slower. So in cases, for example, if we have the FDIF that is running a little bit faster in phase than FREF, then PFD will output a negative value, and then charge pump and loop field will charge down the control voltage and make the VCO run slower. Likewise, if FDIF is slower, then it will make the VCO move faster. So since this is a negative feedback system, if you loop up like this and everything is correct, then it will settle into a steady state after some time. So in a steady state, the input of FREF and FDIF will be phase inlined. You know, the rising edge will be inlined, and as a result, frequency will be the same. And the output will be a zero value, whatever value that will not alter the control voltage here. And in that case, your VCO frequency will be fixed, and that frequency is phase in lock with this crystal. So that's how we will achieve phase lock. Within these phase lock loops, the most power consuming components we briefly touched it is the VCO, is the oscillator itself. And the second power consuming component is the divider. So I start with the FBAR phase lock loop design with this topology, very simple, very commonly used charge pump type 2 phase lock loop. Start with oscillator design. So we have FBAR here, sitting here. This is a cross-coupled differential pair topology. We use 2 transistors here as a current bias. Bias the 2 cross-coupled pair in here. These 2 cross-coupled pairs are generating a negative GM. That negative GM is needed for sustaining oscillation. So basically, keep charging up the energy into this tank. And these 2 transistors here are varactors and the varying capacitors that's used to tune the resonant frequency so that we can achieve voltage control. The output is an AC coupled capacitance and feed into the divider. The circuit looks a little bit complicated, but in a nutshell, it is a programmable counter, and it counts the pulse output from this VCO, and then selectively give out pulses in a determined fashion, so that the output pulse will be in sync, in synchronization with this one, and the frequency is divided down frequency. The phase frequency detector, it looks into 2 input, the FREF and FDIF, and it give out up pulse or down pulse. So that 2 pulses will be fed into a charge pump. So the charge pump, the principle is you have 2 current source in here, one in here provided by this transistor, current mirror, and the other transistor here. And then the pulse controls this transistor up pulse. When it is active, then this current mirror, the current source will be activated, and it will charge up this output voltage here. When the down pulse is up, then it will charge down through this current source. So this branch is a current mirror. Basically, we want to make sure this up and down current will be matched. This is for consideration of other issues in the phase lock loop design. And this is a current reference, is on-chip current reference. And this block, we did some programming here so that we can change the current in here such that it will change the up and down current, so that we can do some study with the loop, basically change the loop bandwidth and stuff. We tapered up this design in 0.30 micron CMOS, and in order for study purpose comparison, we duplicated the same phase lock loop I just showed that is in here next to this design, this one, but replace this resonator with an LC version resonator. And for comparison, we power these 2 designs at the same level. So let it run at the same power level. Then we observe the spectrum of the 2 phase lock loop output. And LC is on top, and FBAR is at the bottom. So recall earlier we have clean LO and noisy LO, how they look like. And you see this FBAR PL is cleaner, right? And the difference is 30 dB. As expected, the tuning range is lower for FBAR, and simply because the high Q. And the tuning range is around 800 ppm, and it's nearly 100 times smaller than the LC version. Oops. So in summary, I have just demonstrated using a high Q resonator to build your phase lock loops, then we can get a much better power efficiency. Basically, we use the same amount of power, we can control the noise much better. And as a result, because of high Q, we get a low tuning range. In order to make the tuning range a little bit wider, because we need it for application purpose, then we have to increase the tuning range. And that's the next few slides are dedicated to how to do a wide tuning phase lock loop. This models an FBAR resonator. We tune the resonator using a shunt capacitor in here. And we vary the capacitor in here, which is shown here. We vary the capacitor, and then the impedance, the resonance will move down to a lower frequency. That's how we do the tuning. as a result, because FBAR has is very sensitive to this kind of tuning, and we can see this this curve. 1 CL at a smaller value, the sensitivity is higher than 1 CL is higher. So that means the parasitics is very important in this wider tuning oscillator. So earlier we used varactor, that's the analog version of the control varactor. Basically, it's a MOS and 2 MOS transistors, and we use the MOS capacitance varying with bias. So if we change the voltage, then we get changing current. And we always, when we do this changing capacitance, we always inevitably bring up parasitics into this tank. And that's not very desirable for tuning on FBAR. In LC tuning, the problem also exists, but it affects less about the tuning range. Another option is to use digitally controlled switch capacitor, and that can also achieve tuning capacitance. The way it works is we have a bunch unit capacitors. That capacitor is made of metal-to-metal capacitance in the, on the same wafer, on the same chip. And this is switches. The transistors are switches. So when we switch on the switches, the capacitance will be switched into the switch capacitor array, and the capacitance will be increased. So we simulated this curve in the 0.13 micron process, and we found the tuning ratio is higher, and it is more suitable for FBAR, for wider tuning. Additionally, we also like this idea is because as process improves, we will see the transistors becoming smaller and smaller, and the parasitic capacitance and resistance will, on-chip, when it is switched on, the resistance will be smaller. These are very two parameters that matters the oscillator performance so much. So it is definitely something that we are interested in. In the future, it will be better and better. So I implement this wide tuning VCO using PS oscillator topology, and this is the equivalent circuit. We tune these 2 capacitors in here to tune the resonator, and the 2 capacitors is implemented using this switched capacitor array. There are 2 parameters that we care: the linearity in tuning, and also the quantization of frequency tuning. So we basically did some design tricks. In layout, we have to be able to match those unit capacitors, and we use the thermometer code do the coding so that we'll get a better linearity. So that's the details in there. We tape out this thing in 0.13 micron CMOS and get a tuning range that is 10 times wider than what we used to get in the analog phase lock loop. So now we have a little bit wider, 10 times wider DCO. It's due for all digital phase lock loop. Earlier we know what is an analog PLL. In there, we had a voltage controlled oscillator, and the input is a voltage. It's an analog signal, but in digital version, we had digitally controlled oscillator, and that digital control is a digital word, and basically that digital word controls that switched capacitor array and then tune that frequency. So because that is a digital word, we need to change the loop filter to a digital loop filter, and then charge pump map into a equivalent function in digital domain, and then translate that phase frequency detector to have an output that's digital output instead of an analog output in the analog version. So that's the conceptual view. Conceptually, using digital implementation, there are pros and cons. And before we do it, we know it has pros and cons. The pro is the loop filter is a digital loop filter. So digital loop filter it is small in implementation because of our digital circuitry. It doesn't involve the passives, resistors, capacitors. Those passives are not good, friendly in the CMOS kind of manufacturing. It takes up space. And the other thing is loop filter is configurable with digital implementation. That's also very attractive. The second big thing is the domain shift is good. It scales with the process. What do I mean by scale? If we use a better process, we will have better performance. Basically, the tuning range will be better, the phase noise will be better, power consumption will be better. The bigger disadvantage of doing this is that on top of all the design considerations associated with analog version of phase lock loops, we have to constantly consider fight through this digitization because quantization error introduce elevated phase noise. So if we're not doing carefully, the phase noise will overwhelm this entire system. So that is useless. The second problem is it can be very power hungry if we're not careful in the architecture level, because we can easily plug in a lot of digital functions in there and then consume a lot of power. So here is what I come up with architecture. This is a dividerless loop. It has a very short TDC. Both of the two measures are designed for low power consumption. The feedback has flip-flops that basically is a function that is similar to a divider. It samples the output of the divider of the DCO output, and then given output, the output is synchronized to this output, and then also the output will have the same frequency as F reference. The TDC is a time to digital converter. Basically, I needed to convert the timing difference between these two signals, RF, and the signal we just converted into a digital word. And that digital word will direct your VCO to go which direct, basically faster or slower. So it's a digital word, and digital word is always in the positive domain. So we want to have a negative or positive, and basically you want to cross the 0 point. So we can, in digital implementation, we can easily do add and subtraction, do a rotation, and then get the performance that get the characteristic we want for type 2 phase lock loop. And this is the loop filter in here. So that loop filter output controls the digital controlled oscillator. So we have implemented this design in a 65 nanometer CMOS. The FBAR is wire bonded into this CMOS chip, and the CMOS core, the circuit core, consumes an area of 200 by 200 micron. And here is the layout for this CMOS. The layout, the biggest portion, the biggest part of the block is a digital block, which is using a synthesized design flow. I use the standard cell, and it has the loop filter, it has frequency data, it has a digital, the interface I/O. Through the I/O, we can program the design. Sitting down there is a core of the oscillator. Next to it is a bias generation for this circuit, and we have a time to digital converter sitting on the top. On the edges are the buffers for input and output. So we did a measurement. The result is we got more than 6,000 ppm tuning range, and we got very good phase noise here. And the phase noise can be appreciated much better through this comparison. I use a figure of merit in here, which captures the power that's consumed in the loop and the phase noise that the loop generated. And in here, I actually used jitter instead of phase noise. Jitter and phase noise are equivalent, sort of equivalent in measuring the stability of the sinusoidal signal. So the x-axis shows the power consumption, y shows the jitter. So at this corner, we will have a higher power and end up with lower jitter. So that means the power efficiency is not good, and we certainly don't want to be in that region. And this region is in the other opposite. We have lower power and lower phase noise. And if we put a lot of LC oscillators, on-chip LC phase lock loops, they will fall into this region. We see 2 dots in here. That was from a paper using sub-sampling technique to generate frequency. And those frequencies are a fixed frequency, and it is not tunable. So comparing with all the works out there, this work is more than 5 dB better in terms of the figure of merit.
Just to calibrate myself, at 100 kilohertz offset frequency, what is the phase noise?
Normally we see 100 kilo.
100 kilohertz offset on carrier. That's the number I will compare your number with others.
Okay, let me think a little bit. Okay, usually at 1 megahertz is around 150, 145, and it's 20 dB. At that region, it's 20 dB per decade. Yes. So in summary, I just demonstrate using high quality factor FBAR, we can generate much better power efficiency frequencies. And in the meantime, the high Q FBAR can also provide moderated tuning so that we can use it in low power wireless sensors. So what am I going to do next? The goal of my research is to realize low power autonomous wireless sensing. Here I show just a little bit of flavor from some other people's work. It is a very primitive wireless sensor. It is built up completely from off-chip components. One of them is there are transceivers. You can wireless transceivers. You have temperature sensor built in there. So basically, this guy can transmit a temperature reading in every 15 seconds, and it consumes 10 microwatt of power. And all this power is provided by this energy harvester here. This is a vibration harvester. So wireless sensors in my mind should have sensing, multi-parameter sensing, should have data processing, communication, and should have energy harvesting. So to get there, we have a lot of things to do, but right now I can only think about directions like this, 3 directions. One is try all the ways or possible ways to generate frequencies without using a quartz crystal. So because quartz crystal is very large, bulky, it takes up space, and that is not very suitable for small devices, for small wireless sensors. So one of the possible way of doing this is to use MEMS to replace quartz, because MEMS has a high quality factor. That's one thing. The other thing is it is small in size, and the other thing is compatible with the manufacturing process is compatible with CMOS. So basically, we can integrate this device with CMOS on the chip level or on the wafer level. So this is of great interest to industry because this can greatly reduce the cost for system builders. The second biggest area I want to focus on is to explore low power RF design. So one of the most challenging project probably is the wireless neuron recorder. So probably everybody here is very familiar in this subject. Neuron scientists like to simultaneously to monitor the activities of hundreds of neurons. And the amount of data that a neuron generates for this recorder to handle is like a Wi-Fi, basically the data traffic. So do you think about you plug this Wi-Fi into your skull, and you are limited in the size under 1 centimeter, and you are not going to overheat your scalp. So that's a very challenging project. So I would very much like to use this kind of application to drive as a driving vehicle to study and to push the limit of low power RF design. The third direction is low power interface circuit. And those interface circuit interfaces the sensors, all kinds of different sensors. And I believe this involves a big area, and we need requires a lot of cooperations with professors and scientists who has experts in how to make those sensors and how to understand how the sensor works. And wireless sensors won't be interesting unless we are equipped with very smart, innovative sensors and find very good applications. So in summary, I would like to draw 4 points. One is I shown that the wireless sensors need very low power, and there's a very harsh kind of power constraint on the circuit side. FBAR PLL creates a very good platform for generating a very good frequency with low power consumption. And the third point is the co-design, FBAR and CMOS, is very suitable for this type of wireless sensor applications because it can be easily integrated, it's small, and the benefit that using it is overwhelming. And the last point is in the future wireless sensor, we need more innovative designs in circuits, and we need more collaborations with many different fields. Thanks for your attention.
Okay. Question?
Well, first of all, thank you very much for your presentation. I think that's quite a potential for some of the applications you could be using it. Something that I would be interested in is, did you do any work trying to analyze the robustness of the chips that you've been working on in real-world settings? So how do they perform, when exposed to EMC or ESD type settings when you have low quality power driving the chip? How do they respond in those environments? Or if you haven't done it, what are your plans for comparing these? So that you can get beyond sort of just the metrics on the academic side, something that helps to evaluate how useful it can be in the kind of applications that you're looking at.
So the question, I'm not sure I fully, is it really far? So basically it's an integration issue, how reliably we can integrate FBAR with CMOS.
Well, the question is how reliable are your chips with your technology when, seen in a system setting where your power supply is maybe not a $20,000 lab supply, but very poor quality inductively coupled power that goes into the system.
Yes.
And the setting is such that you have all sorts of 50 hertz noise and electromagnetic compatibility.
Okay. Yeah, that's rather yes. That's a rather generic question. For that question, actually, that problem actually exists in all electronics. Yeah. People spend. Every company has a big team doing power management, trying to make your supply as stable as possible, so that your circuit will not screw up. So yeah, that's a very realistic problem. And in my work, I didn't focus on that area, but I can foresee that can be a problem for student design. A lot of design is fully outside, and it won't sustain for a long time, and it's very susceptible. So when we do experiments, I don't see usually, when people are walking around, you definitely don't want to do measurement. So basically. Need a setting to especially in this kind of higher frequency. Yeah.
Well, I think another way to ask is what happens if you change the VDD and the temperature? How how sensitive is the freewheeling seal? I mean, these are.
Yes, that's a very good question. Yeah, the temperature stability. I have shown two designs here. One is a differential. Another is Pierce. I did some other things that I didn't present here. My experiences with temperature, basically, the stability inherits whatever stability you have in the resonator. So if we use a better resonator, like a temperature compensated resonator, we can probably observe 3 ppm per degree C, that kind of range. And that's worse than we see when we just measure the bare FBAR dye. So CMOS actually couples some temperature things into this circuit.
That was, I guess, a follow-up discussion.
Okay.
So I had a few, I guess, detailed questions. One is, one of your slides showed the limited tuning range, and you said that you cannot achieve a large tuning range, but if you remember correctly, it was due to the high Q of the inductor.
Right.
Then you change the scheme, rather than using the reactor, you use the switch capacitor.
Right.
Now, that didn't change the inductor Q.
That's a very good point. Yes.
How did you achieve large tuning range?
Yes. That's what I showed in a couple of slides here. You see this slide? Okay. Here. So we basically, when it is in FBAR, we basically limited the maximum tuning range you can obtain. Is okay. You cannot get all the way to here. In between this, you have maximum probably 30 or 20 megahertz. That's the maximum. With the LC, you don't have this kind of constraint. You can tune like 30% of your whatever frequency. It is always spread up to here. So that kind of characteristic is less sensitive to the capacitance loading to here. So in here, you load the capacitor. If you don't care what it does and just load the capacitor, the oscillator will not run. So basically, it will completely overload this structure. Basically, move the curves further down to here somewhere, and then it lose gain, and the oscillator loses the gain, and then you don't get oscillation at all. So with LC, we don't have that problem. So the reason why I can get a better tuning range.
With the LC, you have the same problem, but the LC
it's less severe.
So your phase is not as sharp. Right?
Yes, it has this problem, but it's not as severe as what we're seeing here.
Another question is, you tend to you use a 65 nanometer process.
Right.
And what is your load of Q, the quality factor, using this high Q inductor? What is the 65 nanometer transistors versus unloaded traditional LC tank?
Yes, that is a really, really very good question. Basically, when you move up to a better process, transistor size becomes smaller and smaller. Your transistor is less ideal. Basically, you have smaller R out, and that smaller R out will overload that tank. So basically, it will reduce the quality factor of the tank. So the way we do it is we use an RP, like basically, if you will use a very, very high RP kind of resonator, you will see more degradation in quality factor. But if you use a smaller one, then you will see less degradation. So basically, usually I use the RP at around 2,000 ohm.
How much current do you run?
In the oscillator? In the oscillator, usually it's like around hundreds of micro. So yeah. So the loading is like in CMOS, in the better CMOS, then we see more loading in there. We have to be very careful. Yeah. it turns out that the biggest problem in 65 is not about a smaller R out. It is the leakage, the gate leakage. I found gate leakage is really, really a problem in designing these oscillators.
Last two questions. How much inductance you get from the FBAR?
How much inductance you get from FBAR?
Yeah.
It's around, I used 1.5 gigahertz kind of resonator. It's about 70 nano, 80 nano, yeah, or 60, around that range.
Other questions?
I just making late. Did you make the FBAR or what did you get FBAR for?
Yes, we just we have a long time kind of collaboration with a company called Avago, Avago Technology. I have a chronology here. And this is our sponsor. In my work, I basically use their resonators. And some of the resonators, most of the resonators actually is commercially available, and they're very reliable. But the bad things, it works. Absolutely, it will work. But I see some problems. For example, we raised that issue RP. Okay, I don't want so big RP. I want lower. But sometimes they just give me a higher one, so I have no choice. And some other parameters as well will concern. As circuit designers, we know exactly what kind of resonator we are looking for, but sometimes we don't have that kind of freedom. Yeah. So your question is around that loop.
I was trying to understand where you can buy that same assemble with off-the-shelf parts rather than being cheap.
Absolutely. People, when I was in Agilent, people build up their instrument. They have tons of phase log loops over there. Every instrument has, 10 or... Yeah, PLC is made of components. The reason they use off components is because they get better performance. They can get very good phase detector. They are not limited in the CMOS, because CMOS is a kind of crappy, cheap process. So by doing that, they have freedom to choose. Better VCO, they can crank a lot of power. They can...
I think the question was, can you find that CP3 with off-the-shelf parts with FBARs?
With FMOS?
With FBARs, with the FBAR.
With FBAR. Oh, that's a good question. Okay, FBAR. FBAR is available on the market, but it appears as most time is filters.
Okay.
They don't sell individual resonators.
They don't sell it as a, okay.
Yeah. Yeah. Sorry.
You just made a point. FBARs are usually commercially available as filters, right?
Yes.
Like surface acoustic wave filter, and they have like S1 of -25 dB. It's basically the frequency selectivity that determines your resonance, right? So how do you achieve that low power together using such filters?
My understanding is you use. Can you repeat that question again?
Like if I look at a FBAR filter, the S1 is like -25 dB, right?
-25 dB. You mean the loss?
Yeah. So
is that so high?
Yeah.
Or maybe -2 dB or something?
No.
-25? Okay. Well, the more dB you lost, that means you have a low quality factor. So one quality...
In commercial, you do get notch filters which are like 1 megahertz at 2 gigahertz, right?
Yeah.
Bandwidth
Yeah.
at 2 gigahertz.
Yeah.
Having a loss of -25 dB.
Yeah, the way you construct it is differently, because the filter is a completely passive device. So basically, you go through the signal, and then you see signal, it's been attenuated. But with oscillator, you are not using the same way as you build the filter. So you have to generate positive feedback so that it will do oscillate. Basically, you need power to do this kind of signal generation. I don't know.
With conventional technology, then you are actually pumping more power to your filter.
Your intuition is good. If you have a big loss in your filter, and then you use that filter, just completely dismantle that filter, use that resonator in the filter for oscillator design, then that means that Q factor actually is low if you see the big loss. And then low Q corresponds to higher power in oscillator design. That is consistent in theory. So, yeah.
Any other questions? Okay, in that case, let's thank our speaker again.